Hey everyone, my name is Smriti, and today I'll be covering the first question on the asymptotics worksheet for week 6. Before we get started with the problem, I do want to say asymptotics are definitely a really hard topic, so if you have any confusion with anything I go over today, definitely reach out to your CSM mentor and ask them for a little more guidance. Awesome. Cool, so the first question asks you to define in your own words each of the following asymptotic notations. So here we have big O, omega, and theta. So before we jump into this problem, what are asymptotics? Asymptotics are super important because they essentially, as it says up here in the worksheet, it's a method of describing the runtime of an algorithm with respect to the size of its input. And so why does this matter, right? If you look at, like, for instance, a Google search, if a Google search could take 5 seconds to run, but a Bing search took like 5 minutes to run, which program would people more want to use, right? They'd want to go to Google over Bing because their search could be done much faster with Google than it could be with Bing. Similarly, we really want our programs, especially in industry, to run faster on average. And so that's why asymptotics really matter, especially when we're writing code that's efficient, to make sure that it is running in a reasonable amount of time for larger scale inputs. So asymptotics is always, when we're computing them, we're always looking at huge inputs. That is one thing to note. So for instance here, if n is your input number, you're always going to want to look at like huge n's rather than like n being 1, 2, or 3. And so we have a couple of formulas written below that you guys will probably get to later on in this worksheet, where there are some common sequences that's kind of nice to know. So if a problem follows one of those sequences, then you can kind of know what the runtime of it should be. Awesome. So if we go back to this question of defining each of the following asymptotic notations, first let's start with big O. So for big O, this is going to be an upper bound on your runtime. And so I've drawn out 3 graphs on the right here. So if we say that this first one is going to be big O, so if this is your function f of x, a big O bound will actually kind of look like this, where it is an upper bound on the runtime of your function. And so f of x will never exceed the runtime of your big O bound. And one thing to note here is that actually faster growing functions are slower. So like you don't want to have a faster growing function, for instance, like n squared, right? If you have a runtime of big O of n squared, this is worse than a big O of log n. And in a graph, right, your n squared is going to grow like much faster than your log n. And so this is going to be a worse runtime than this one. So yeah, that's just one thing to note. And so big O is going to be an upper bound on your function. So if you say the upper bound of my function is n squared, then my function will never grow faster than n squared. So it'll never be slower than n squared to run a program. So you could, for instance, never have big O of n cubed be basically the runtime of your function if your big O bound is n squared. Awesome. So yeah, this is an upper bound. If we move on to the next one here, we have our theta bound. And so our theta, oh, another thing to note is it's an upper bound as your function approaches infinity. So as the size of your input approaches infinity. And this is true for all of the bounds that we're going to talk about today. It's always as the size of the input approaches infinity because we're looking at huge n's rather than smaller ones. So for omega, it's going to be a lower bound. So let's do this in a different color. And the same thing as your input approaches infinity. And so we have our omega graph right here, right? The second one. So if your function is f of x, this is going to be a lower bound. And so essentially, your function will never be faster than your omega bound. So for instance, if your omega is n, your function will never like run in constant time. Like it's never going to be, that's like the lowest bound for the runtime of your function. Awesome. So the theta, let's write this in a different color as well. This one gives a tight bound on the runtime of your function. So tight bound. What does this mean? A tight bound means that your best and your upper bound and your lower bound kind of converge and they're the same. And so if your upper bound and your lower bound are the exact same, then you can actually give it a theta bound. So for instance, if the upper bound of your function is big O of n and the lower bound of your function is theta of n, you don't have to write out both of these. You can just say your function is bounded by a theta of n. And so here, like what we can see is like these two, like this red and this blue are going to converge to your bound, to like your theta bound. So you can just say like your function is a tight bound of theta as your input approaches infinity. Awesome. So that was 1.1. Now let's move on to 1.2, which asks us to give a tight asymptotic runtime bound. So the first thing when I look at this question, I see it asks for a tight bound. And we talked about earlier that a tight bound is our theta. So we're going to look at theta of n in your best case, your worst case, and overall. And so here you guys might be getting a little confused by the notation because we previously learned that our theta is a tight bound. And it's when our big O and our omega kind of are the same. And so here we're actually looking at best case, worst case, and overall of our tight bound. So even within theta, you can have a best case scenario and a worst case scenario. And so that's kind of what we're looking at. And I wouldn't get that confused with your upper and lower bounds, which is your big O and your omega bounds. Awesome. So with that kind of clarified, let's look at this actual code. So here we see our int list is defined and we have a first and a rest, and contains is essentially checking whether our linked list our int list contains the value that's specified. So we're traversing this list. So if we want to first look at our best case scenario, we're looking for a theta bound on the best case. And we can see here that in our first statement, in our function, if first is equal to value, then we're just going to return true. So in our actual best case, we're actually going to get a linked list that kind of looks like this. So let's say this is our linked list. So this is 1 and 2. And you're looking for the value 1. Then it's just going to look at the first element, find that it's 1, and then return true. So in your best case, this can actually be done in constant time, where you just have to like look at one element and you're done. So that's why our best case is actually going to be theta 1. And then if you look at the worst case scenario, if our value that we were actually looking for is 2, and the size of our linked list is n, which is equal to 2, you're actually going to have to traverse the entire list to find 2, right? So you're first going to have to look at this 1. If I highlight it, we're going to look at this element first, then we're going to move on and check this element. And if our list was even longer, this would keep going until you find the nth element. So if our value is the last element in our linked list, that's essentially the worst case because you have to iterate through all the previous values in order to find it. And so that's why in our worst case, our runtime is going to be theta of n. And then if you have our overall runtime, since we can't give a theta bound for overall, we can actually just give a big O or an upper bound for overall. And so we can say that this is going to be big O of n overall. Awesome. Yeah, and so that is all of question 1. If you have any questions about anything I talked about today, as I said in the beginning, definitely reach out to your CSM mentors. But otherwise, I will see you at the next walkthrough.